My name's Nick Camiotti.
I'm Biscatus.
And we're going to be teaching you about Newton's 3 laws.
Roll Tide.
Roll Tide.
Getting water to take the horses.
Roll Tide.
What?
When the golf cart is moving, the barrel moves with the same velocity. When the brakes are hit, the barrel continues to move until acted upon by the outside force, the ground. This demonstrates Newton's first law that an object in motion will stay in motion unless acted upon by an outside force.
Unfortunately, Nate's car just broke down in the driveway. The tide is not rolling. Thanks to Newton's second law, though, F equals ma. With more force, an object of greater mass can be moved with more acceleration.
God, Biscatus is taking forever.
I don't know,
We need to get down this driveway.
I know. We're late.
While we're waiting, you guys want to listen to some music?
Roll Tide.
Roll Tide. Roll Tide.
Yeah, I think I got a little something here. Let's see what I got.
I threw a wish in the well. Don't ask me, I'll never tell. I looked to you as it fell, and now you're in my way. I trade my soul for a wish, pennies and dimes for a kiss. Where you think you're going, baby? Hey, I just met you, and this is crazy, but here's my number, so call me maybe.
Stop the music!
Call me maybe.
Not Roll Tide, man.
Get out here and help me push. With a greater force, there's greater acceleration.
Roll Tide. Roll Tide.
Roll Tide.
It's such a good song, though.
It is. It's great.
Ready?
Go! Oh yeah.
Oh, yeah.
Oh yeah. Oh yeah.
Wait, who's steering the car?
Oh no.
All right. You know what? I think you guys got it. Come here.
Newton's third law explains the concept of equal and opposite reaction. Check out this YouTube clip. Roll Tide.
Roll Tide.
I have nothing for you. Stop.
Here are many microbeads on a metal surface which provide a very low rolling friction for a metal sled to move on. A rubber band is being used to attach the sled to a launching mechanism. The rubber band has tension so that when it is cut, it's going to launch the metal sled. This is a demonstration of Newton's third law of motion. For every action, there's an equal and opposite reaction. So the action of the rubber band pushing on the metal sled launches the sled to the right, and the launching mechanism is the equal and opposite reaction is going to go to the left. Now you can see the metal sled launching to the right goes twice as fast as the launching mechanism. That's because it has half as much mass as the launching mechanism.
Welcome back to Roll Tide Physics. Next up, we're going to be talking about momentum. Momentum involves mass in motion. So any object has mass, and if it has motion, it has velocity. Momentum is expressed by the equation P equals mv, where P represents momentum, m represents mass, and v represents velocity. When you multiply mass times velocity, you get momentum. Thus, if there's an object that has a higher mass and is going faster, it's going to have a higher momentum. But if you look behind me, you'll see Momentum Man running in a very fast pace, and he's quite massive. Whereas Biscatus, not as massive, probably not running quite as fast. Thus, Momentum Man has a higher momentum and will be able to tackle Biscatus. Eventually.
Hi, I'm Momentum Man, and as you can tell, I am quite massive. Biscatus, on the other hand here, not so massive. Let's find out when we come into a collision.
When Momentum Man collides with Biscatus, you notice that his momentum is then transferred to Biscatus. Biscatus then goes flying. This again happens when he bumps into Nick. This is known as the conservation of momentum. This YouTube clip involving an astronaut is a great explanation of how this concept works.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same.
In our example, Nick can be compared to the tennis ball that is not moving. He has a momentum of 0 because his velocity is 0. When Anthony comes along with a large momentum, his momentum is then transferred into Nick. You can clearly see Nick speed up and Anthony slow down as his momentum is transferred into Nick.
The higher momentum an object has, the more difficult it is to stop the object. Since we know that momentum is affected by mass, we set up the following demonstration.
Allowing ample distance for the cart to hit top speed, we marked a spot for Anthony to hit the brakes, and we marked the distance it took him to stop.
We then filled a large barrel of water with a significantly heavy amount of water and placed it in the cart. Keeping the velocity the same, but by adding more mass, we had raised the cart's momentum.
When Anthony slammed on the brakes this time, it took a greater distance for him to stop completely. To ensure accuracy, we did a second trial with the same result. The barrel of water had successfully increased the cart's momentum. Roll Tide.
Thanks for watching this episode of Roll Tide Physics. Me and my friend Al Capone here really enjoyed your company. We're going this way apparently, but remember, physics is fun, and roll tide. Whoa.
An object of greater mass can be moved with greater acceleration with more force.
That didn't make any sense.
You guys want to listen to some music?
Roll Tide.
Roll Tide.
Roll Tide.
Let's see what I got here. Oh, this is awkward.
I was like,
it's not playing.
Gosh, Biscatus is taking forever. He'll be hurt.
Biscatus, we have a serious problem here. We got a serious problem here, Biscatus. Whoa! Whoa!
Momentum can be described as mass in motion. Oh, I messed up. Momentum can be described as mass times velocity.
Momentum!
I can't focus on that.
Don't tackle me.
Tackle him.
Don't tackle me.
Momentum! Momentum!
Alright, starting. Drag it. Oh god. Water everywhere. No! That's it. That's good enough. God, Jesus, that got all over me. Stupid barrel. It's not roll tide. Not roll tide.
Now it's roll tide.
Yes. Oh, roll tide.